Okay, good evening and welcome to Measurement Part 2. So, I've already written out a few notes for today. We'll get through those as quick as we can and then we'll move on to the next one. So we're going to start off with talking about mass. And mass is how much stuff you have. So it's the amount of matter. Right? We talked about what matter was. Earlier this week we had a reading assignment on matter. So hopefully you remember what that is, right? Matter is anything that has mass and takes up space. So it has weight. The gravity affects it. And weight's different than mass. We measure mass in kilograms. So kilograms is the amount of matter. And we use kilograms, we don't use grams. And just like a kilometer is 1,000 meters, a kilogram is 1,000 grams. And in chemistry, you use grams a lot. In biology, you use grams a lot, but in physics we use kilograms because we tend to be dealing with bigger things. Weight, like I said, weight is different. Weight is the force of gravity on an object. And the force of gravity on you depends on where you are in the universe. So here close to the Earth pulls down on you pretty hard. But as you go to the moon, the Earth's force on you is much less, but the moon's force is much stronger. But it's not as strong as the Earth, so your weight has changed. So it changes as you move around. There's always weight, you're never weightless. It's one of those common misconceptions, and we'll always talk about why that is. You always have weight, it's just that it can be very small depending on where you're at. Also related to mass, and different than weight, is something called inertia. And inertia is different in that it's how easy or difficult it is to get something to either move or stop. Or you can even add change direction in there too. So how easy it is to get something going or bring it to a stop. And obviously, bigger things are harder to get moving than little things. Things with more mass. So that's what a lot of times we talk about with mass. We talk about inertial mass. Because inertia is always the same. No matter where you are in the universe, your amount of inertia you have, how easy or difficult it is to get you to move, is always the same. So your weight can change, your inertia doesn't, and they both depend on mass. Okay? So, that's the last little bit of the stuff we need to talk about with measurement. Well, let's talk about scientific notation. So when we did that math review, there were some questions at the bottom, like how many thousands is 4,500? And that's related to scientific notation. Because scientific notation is a way of taking big numbers that are difficult to deal with and making them easier to deal with and making the math easier. And it also helps us when we're looking at something called significant figures and rounding. And we'll get to that probably early next week. So if I have a number like 150 billion, that's 150,000,000, which I've written down there, and I need to convert that into scientific notation, there's a series of steps that I'm going to follow. So the first thing I want to do is move the decimal point so that my number is between 1 and 10. So I took that decimal point at the red spot and I moved it over to the black decimal point, which gave me 1.5. Second, I want to write the number without the zeros. So I wrote it down, 1.5. That's what I did in the green there. After I write down the number without the zeros, I write times 10. And I did that in black. The fourth step is I write the exponent. And you write the exponent next to the 10, and it's always just the number of times you move the decimal. In the case of 150 billion, I move the decimal 8 times to the left. So it's 8. In the example below that, I had 0.0025. There, I moved the decimal to the right so that it was between the 2 and the 5. So I wrote 2.5 times 10. And then I had to do my exponent. So I counted the spots and I moved it. And you can look and see I moved it 1, 2, 3 spots to the right. So my exponent's 3. But because I moved it to the right, the exponent is negative. So a negative exponent means a number less than 1 but bigger than 0. And a positive exponent means a number bigger than 1. So I can do a couple more examples here. We've got a little bit more space. So looking here, and we can write 3, 5, 1, 0, 0, 2, 0, 0. Okay. So I just made up a number. So the first step I got to do is move the decimal point so that my number is in between 1 and 10. So I'm going to put it right there. And I'm going to rewrite it without any zeros. And this is why I did this, without the trailing zeros. Those middle zeros hold places. They are important. They need to stay there. 3, 5, 1, 0, 0, 2. Times 10. And then how many spots did I move it to the left? I moved it 1, 2, 3, 4, 5, 6, 7. Times 10 to the 7th. And that's it. And now it's in scientific notation. And in this situation, maybe it doesn't make so much sense to go with scientific notation because we only got rid of 2 zeros. But if you're dealing with something like 6, 2, 3, 2, 3, 4, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That's a lot of numbers. That is much easier to write like this. 6.23 times 10 to the 23rd. Okay, so when we're dealing with very large numbers, like the speed of light, that's very fast. You know, it makes it much easier to write it in scientific notation. And scientific notation also is easy to work with when we're doing our dimensional analysis like we've done in the past. So let's throw out a few terms that are important when we're talking about experiments. As we move forward, we're going to start looking at different experiments that are out there. We're going to start conducting experiments. We're going to talk about our equipment. And there are 2 words that people mix up a lot, and I always like to make sure I make them clear. And these are also 2 words that are up on the word wall. And actually, all of these words that we're going to talk about right now are up on our word wall in class, which means you're going to need to be familiar with them, and you're going to need to know how to use them. So the first one is accuracy. And when something is accurate, it gets a close to correct answer. So it's close to the true value. So if a scale is accurate, it tells you how much mass you have. It tells you, or if you're at the gym, right, it's going to tell you your weight. And if your scale's not accurate, then it's not really useful. So we need accurate equipment, but we also want equipment that's appropriately precise. Like yesterday in the lab, our graduated cylinders could measure up to 100 milliliters, and they were as precise as 1 milliliter. If you looked at the beakers, they were also marked in milliliters, but they were only precise at 25 milliliters, so they were not as precise as the graduated cylinder. So when we measure volume of liquids, we like to use a graduated cylinder over a beaker. And then you can think about that too, right? If you need to measure out a quarter of a cup, you don't want to take a 1 cup scoop and try and measure a quarter of a cup. You want to do something that's marked at a quarter of a cup when you're making a baking recipe. You want something that's precise. And when you look at a meter stick, like I've drawn here, I've just drawn the very end of it. If you count off, there are 4 little ticks, then there's a long one, then there's 4 more little ticks, and then there's the 1 centimeter. Each one of those little ticks is 1 millimeter. So a meter stick is precise to 1 millimeter, or 0.001 meters. A variable, when we start talking about experiments, these are any sort of things in experiments, factors that can impact results. So anything that can have an effect on the results is a variable. And we want to limit our variables that we change. We only want to have 1, and that's why I wrote the 1 next to experimental value that you change. And you change it on purpose. And it could be something like time. Right? If we're talking about a car driving down the road and we want to see how far it travels, well then time is experimental variable. It's the thing that's changing. The control variable would be the car, the road, all those other things we keep the same. We don't change the level of the road if we're trying to see how fast the car can accelerate. We keep all those other controls the same. And that minimizes our mistakes in our lab. And it allows us to say, this had an impact or not. So it's always important. Anytime we do experiments, you always want to make sure that you keep everything the same except for one thing. And that one thing is that experimental variable or the independent variable. All right, I think that's a good spot to stop. And we will pick up another time with the rest of our notes. So I will see you then.